My name is Sura Wang. I'm currently a second-year student at Carnegie Mellon University. And in general, my research interest is building language models with interpretable and generalizable reasoning skills. And one particular application of that is code generation. So today I'm gonna mainly talk about my recent work on execution-based evaluation for open domain code generation. Yeah, I think I'll stop for 1 or 2 times during the talk, and feel free to pop up any questions if you have any. So with that, I'll start with the talk. So I think probably most of you have been using the GitHub Copilot in either your VS Code or other code writing platforms. And it's at least personally for me, it's very helpful and helps me write code more efficiently. But the recent query that we have is does the GitHub Copilot or similar program assistants always help? The answer is probably not. So we identified 2 cases that is still not doing very good on. The one is that sometimes when you're trying to write very complex code where it involves a rare library, that it might fail sometimes. So I'm showing an example on the right here that I wrote the comment here, send an HTTP headers to the client, where it requires a additional library. And instead of using the client send function, that the Copilot actually predicts the client get function, which is not correct. So we're formulating denoting this type of complex where code that involves external libraries is open domain code, which on the opposite for the closed domain code, we're referring to code that only uses the Python built-in grammars. So the first issue of the current program assistance that for open domain coding queries that it's not performing as well as the closed domain queries. And the second issue is that we are when we're writing code, we're unaware of the errors until we actually execute that piece of code. The example that I'm showing on the right bottom here is that humans are not perfect programmers as well. And sometimes when we write code, we it looks like it's correct and it doesn't have any syntax errors. When we actually execute that piece of code, it's popping up the error message. So the more rigorous and effective way of evaluating whether a piece of code is correct is probably execution-based evaluation. And for that, we probably need some unit test cases to execute that generated piece of code solution. So in summary, these are the 2 main issues that we're aiming to tackle in this work. Basically, we're targeting on the open domain coding queries, and we're focusing on the execution-based evaluation. So just an overview for the work. So we one of the motivations we want to further challenge the code language models. We're trying to improve it on more complex scenarios. And to do this, we first propose our ODEX dataset, which stands for Open Domain Execution-Based Evaluation Code Generation Dataset. And based on this built dataset, we also use it as a test bed to study the different behaviors between state-of-the-art code generation models. And also we did a bunch of ablation studies to see what are the influencing factors for those models' performance. So I'll dig into each of the sections in the following this talk. So first, start with the ODEX dataset. Here's a overview picture of what this dataset looks like. I'm showing 4 examples here. So on the left is the like input side, and on the right is the output side. So for the input side, we like specify the libraries that are probably gonna used for this example. And then we also have a doc string that includes a natural language instruction. Um, and here, like the gray boxes are like slots leave for the model to like generate and fill in the code solution. And on the right side, like here we put the canonical code solution into the gray box to show like what could be a good generated piece of code. And then another like the main annotation that we're doing is that we wrote test cases for all of these samples that we're gonna evaluate. So you can see like they vary a lot from case to case. And sometimes for more complicated cases, we might need to use more advanced techniques like writing mocks. And also there are some like randomized outputs, which I'll further discuss. And we were like talking about the test case annotation. So starting with the source of our datasets, we're collecting the datasets from the Stack Overflow forms, which is like borrower observations, probably the most realistic data source for Python code. So here's a like snapshot from the Stack Overflow developers survey in 2022. So you can see that only less than 1% of the respondents have never visited Stack Overflow forums. So which demonstrate that it's like a very commonly used resource for developers. And it's not only like targeting the English developers, like English developers whose native language is English. There are also other language versions of the Stack Overflow forums, which includes Japanese, English, Spanish, and Russian. I'm showing several examples of the intents that we extracted from the Stack Overflow forums in these 4 different languages. So one like valuable feature we have for our data sets when we're deciding what resources to take is we consider multiple natural language as the input, which not only facilitates the like English speaking developers, but also potentially helpful for other developers who are more comfortable speaking other languages.
Zora, sorry.
Yeah.
If I could please ask you to maybe speak a little bit slower, because not all of our colleagues are very well versed in English. Say, my English is not perfect. So if you could just speak a little bit slower, I guess people would have better chance to understand.
Okay.
It's not
Okay,
that there are
cool.
any problems with the language, just that it might be a little bit too fast to say for me.
Okay, just to make sure that I understand correctly, just I can I can speak slower.
Yeah, a little bit slower,
Okay.
if you could, please.
Yeah, of course. Cool. So yeah, this slide basically introduce our resource for the collecting the coding queries, which is Stack Overflow forms. And the next interesting feature of our dataset is its open domain property. That by open domain, we are like building this concept against an opposite to the closed domain coding queries, which I'm showing 2 examples. On the left is a like open domain coding example, and on the right is a closed domain example. So for the closed domain example, we mainly refer to those code that only uses the Python built-in grammar, such as numerical operations or string manipulations. As you can see from the example on the right, that it's basically just like a list comprehension with some like add operation, which is like probably too simplified as compared to the code that we as developers would write in our daily lives. Like in contrast, on the left, I'm showing like an open domain code inquiry, which first involves additional usage of external libraries. In this case, is the request library, and then also like on the like evaluation side is more complex. That for this specific case, that when you're sending it, so like what this code example does is that it sends a HTTP request to the URL shown here. So the issue for this example is that it might not be correctly executed every time when we're like executing this piece of code, where it's not fully reproducible because it's not reasonable to continuously sending a request to this website because it is included in our dataset. So instead, we like choose to write a mock function in the task case to mock the correct like return value when we're actually sending that piece of request. So like in general, the open domain code requires more complex other code solutions and also more complex task cases to correctly evaluate and generate those. And for our ODEX datasets, we cover 79 different libraries. As you can see from the bar chart here, that like more than half of the examples are used in one or more external libraries, and they have like different purposes. Some of them are data science libraries such as pandas and NumPy, but others are say like web requests such as the HTTP requests or BS4. Like comparing to all the like closed domain or previous code generation datasets, as I'm showing on the bottom right here, that you can see from the like length of the blue bars here that almost around 90% or more of the datasets only includes the closed domain coding queries. And they have very limited amount of external libraries involved, which are not necessarily a realistic scenario or like test bed for the daily Python program that we are writing. So we're highlighting the open domain feature of our ODEX dataset to simulate the real world coding cases. And the third feature is that we support execution-based evaluation. So a little bit of the background is that like, I think probably 2 years ago that most evaluation for code generation works are using lexical-based evaluation like Blue, Rouge. Those, although they can measure the like surface form similarity between the two pieces of code, but that does not guarantee the functional correctness of those code solutions. So the more rigorous approach is execution-based evaluation, mainly that given the piece of code solution generated by the model, we have several test cases, and the code solutions then executed over those test cases, and we like check if the model execution output meets our specified output to see if those are actually correct. So on the right, it shows an example of how we're writing, like annotating the test cases for our open domain coding queries. So it involves 4 steps. The first is that given the like single line or like a solution, we first wrap it into like a function format so as we could easily specify the input and output variables to facilitate the execution. And the second is that we import the necessary libraries involved in this case. And then our human annotators write the test cases to basically to specify the input and call that function that we previously wrapped for our code solution, and then check if the execution outputs meets the specified output. And we ensure the quality of our test cases by executing the canonical code solutions on those test cases to make sure that they have like a 100% pass rate. And there are like some interesting, unique challenges that we encountered when we're annotating the test cases. One case is that, as I previously mentioned in the last slide, not all of the executions are reproducible or like reasonable to execute every time. So for these cases, we write mock operations. And the second scenario is for the randomized outputs that this is particularly for the random library, but also other similar functions like numpy.random, that when you're generating, say, a random real value number, is not, you cannot, it's impossible to exert a strict match of the output because you don't know which specific number that it will output. So for this, we will, our solution is to write like multiple boundary test cases to check whether the is like execute is functionally correct. For example, when we're writing code to generate a random number between 0 and 1, our test case might be to check if the value output value is within the range of 0 and 1. And the third case is the domain-specific equivalence check. So for previous works, when they're writing test cases, and also related to their closed domain nature, that we can just simply write, like if we want to check two arrays are equal, we just write assert A equals B. But that does not always work for open domain coding queries. For example, if we have two NumPy arrays, that like simply using the assert function is gonna report value error because that is not supported for NumPy arrays. And instead, we need to use the domain-specific function to check, which is numpy.array equal, to check their equivalence. So these are the three unique challenges that we're proposing alternative solutions to while we're annotating the test cases. Yeah, so these are the about like the construction process of our ODEX dataset. Any questions so far?
So please, folks, raise your hand if you have a question. And meanwhile, while your folks are making up their mind, I guess I would like to ask a question of my own. So there could be an option that there is some interesting, say, library that would be developed recently and would not be a part of database of code base on which a large language model would be trained. I don't know, say they release a very nice library, but from scratch. So do you think ODEX would be able to emulate the performance of the LLMs on the previously unseen libraries? Because, I mean, technically LLMs can also take the previous context, and some of them, like GPT-4, is supposed to take a hefty large context. So technically they could possibly be useful even for code, like for doing something with the code, like for using the API of the libraries that never been seen before.
Just to make sure if I understand that correctly, you're asking for like a newly developed or unseen library, is ODEX like
No,
able
no,
to?
Sorry, yeah, let me rephrase. I'm a little bit verbose. So there are closed domain problems which related to Python's syntax itself. You'd extend this by considering a data set of various libraries which are popular in Python but not formally part of Python core. So do you think that performance on ODEX could be a sign on how the large language models would perform on the libraries that they have not seen before for whatever reason?
Uh, you just another clarification. So you're asking if the model's performance on ODEX can be interpreted as the model's performance on unseen libraries.
Yes, and good performance on ODEX could be interpreted as probably good performance on the previously unseen libraries.
Yeah, I think if we know what the training data of those code language models are, we might be able to tell if ODEX performance, if their performance on ODEX can't review the unseen performance. But like one of our baseline model is CODEX, and we actually don't know what data are being used to train the CODEX model. So like we think that it probably CODEX has been trained on many library involved coding queries, especially for example on StackOverflow or on GitHub. But it's hard to tell because we cannot tell if CODEX has been trained on this data. So it has been trained on these libraries. So it's not sure if these libraries are unsynced to them. But there are several results, like I will show that in the like following slides, that even like when we're breaking down the model performance into different libraries, they vary a lot. So that might partially reveal either model is not trained very well on those libraries, where those libraries are actually unseen. Yeah.
Okay, yeah, thank you. And a slightly related question: were were you ever able to see a case in which it looks like the model have is cheating by having seen the answer? Say when I experimented this codex on Hearthstone dataset, I saw that apparently it was trained on Hearthstone, because if I asked codex to write me too many lines for a Hearthstone dataset query, it gave me the answer for problem, say 7, and also started writing answer to problem number 8, which kind of was indicative that it memorized the whole Hearthstone dataset up to a point. Did you see any cases like that, memorizing stuff from Stack Overflow?
No, I didn't observe any very clear signs of that pattern, but just like assumption. I feel like ODEX probably has been trained on some Stack Overflow data, but they might not like have that like clear pattern that you just described, because like Stack Overflow data is a bit noisy. That involves sometimes the error message by the original post, and then like several solutions, and it's a like interweaving text and code. So it's hard to get it like clearly formatted, like natural language code solution test case data. So I think even though they have been trained on Stack Overflow, it's hard like to have a really clear format of those. So yeah, but
So if I could rephrase, it's just because the Stack Overflow data is by itself noisy, and you naturally cleaned it to create a data set. Is that this could be one of the reasons why you did not observe this pattern of memorizing answer to the Stack Overflow question.
Yeah.
All right.
Yeah.
Thank you.
That, mhm.
Okay. Any other questions, folks? Let me check the chat for a sec. Nope, there are none. So, yeah, thank you. Let's maybe carry on.
Yeah, cool. I can continue to the model performance section. So with this data set, we evaluate on state-of-the-art code generation models on our ODEX data set. So the two model families that we've selected are CODEX and CODEGEN. The reason is that they have like very similar and comparable performance on many other code generation data sets. I'm showing an example on their performance on the human evolved data sets that they have like approximately similar performance on like different case in their pass rate. But that's not the same pattern that we observed when evaluating them on ODEX. So on the left shows the CODEX performance, on the right shows the CODEGEN performance. And you can see that like from the height of the bars that CODEX is outperforms CODEGEN by a large margin overall. And however, from another aspect, where disentangling the performance between open and closed domain coding curves, we see that like there's a large gap between open and closed domain performance on ODEX for like each language. But on the right, for the CodeGen model, they have much smaller gaps. And sometimes like their performance on open domain queries even outperforms the closed domain coding queries, which is like the opposite from the CODEX performance. So this is a like interesting result. It shows that even though like CODEX can perform good overall, but it's like as a larger gap between open and closed domain queries. In our ODEX dataset, by including both some of the closed domain and also a wide range of open domain coding queries, is able to reveal such behavioral differences between this code generation models, which especially when they have very similar performance on other datasets. And the second thing is that we also break down the model performance by their individual domains. Here I'm like plotting the like each library as a dot, where the like vertical axis shows their pass rate, and the like horizontal axis shows their approximated frequency of this library being used in writing code. So the red dots are the the most widely used ones in our data set. And there's like one interesting, probably two. One interesting result is that like not all the model is not performing bad on all the libraries. As you can see, there are still some libraries that achieve a very high pass rate. But on the other side, there's no clear pattern of there's no easy way to predict the model performance on individual domains. I listed some potential factors here. One is the frequency of their daily usage. Intuitively, more frequently that library is being used, then the model is more likely to be trained on some data involving those libraries, and then the model might perform better on those. But then on the other hand, it also relates to the complexity of the functions that is provided in that library. Say, like, for example, comparing the random library with the matplotlib library, that even though like the functions supported by random are mostly like numerical, like selecting a random integer or a random real value, but Matplotlib supports more functions with their like different types of plots and also more arguments that you need to specify. So the complexity of the function involved in that library may also affect whether model can achieve a good performance, or like how much effort this model have to pay to learn to perform well on that library. So this might open a like interesting future direction to study what like actually affects the model performance of individual domains. And another like probably unknown thing is like we sometimes don't know the like data that are being used to train codex. So it's hard to tell whether these are like whether these results reflect that they're like zero-shot performance on an unseen library, or just because they're like not as effectively trained on this libraries. And another comparison study that we did is we compare different evaluation metrics. One is execution-based evaluation that were mainly used for our work, and comparing them to lexical or like semantic related evaluation methods. So besides the pass rate at 1, we also consider other 5 lexical-based methods, which are Blue, Rouge, Meteor, CHRF, and CodeBlue. The first analysis that we did is we rank the model performance using these different metrics. So as you can see, this like bigger graph here is the English performance, while on the right, these are like Spanish, Japanese, and Russian. They have pretty much similar patterns, but the most like significant pattern is that the lexical metrics do not always preserve the ranking by the execution-based evaluation. We're sort of treating the execution-based evaluation as a gold standard like correctness result. And sometimes using other metrics would reverse the ranking or change the ranking. And sometimes even they preserve the ranking, their relative difference is not proportional, which means that like lexical-based metrics still do not have like good alignment with the execution-based evaluation. And the second thing that we did is we compare like visualize the variance between the passed and failed code predictions. So basically for each model generated code solution, we're evaluating 2 things. One is their execution correctness, which is a binary sign of whether it is passed or failed. And the second is we evaluate in this graph the blue score, which is a numeric real value between 0 and 1. We're plotting the distributions of their blue score on the passed and failed code solutions. And you can see that like in the middle range, probably starting from blue score 0.1 to like 0.8, there's a huge overlap in the like blue score distribution between passed and failed groups, which means like regardless of it's hard to discriminate passed and failed code solutions when you're just evaluating their blue score, especially when their blue score falls into the middle range. There are some like clear, like extremely clear bars on the 2 ends near 0 and 1, but like that's the only place where the passed and failed groups are differ from each other. So this is the like visualization for the blue score. We also like similarly plot the figures for other 4 metrics, and they all have a similar pattern, which means that there's still some gaps between the execution-based and lexical-based evaluation. Probably an interesting observation is that for all of our experiments, the code blue score are extremely low. Partly because that like our examples don't involve any semantic flow, but in general, where like one maybe slight conclusion is that code blue is not very effective in evaluating code solutions. And lastly, we also did a bunch of other ablation studies to see what are the influencing factors of the model's performance. And like two of them are comparing different number of in-context examples and comparing different number of test cases that we include in the docstring. On the top here, I'm showing an illustration of how we are creating the prompts to the inputs. So we have a like function context that defines the function signature and the input and output values to make sure that everything can be properly formatted and executed. And the middle part are the doc string, where we have a like natural language intent. And also optionally, we will include the task cases that we annotated as a like executable hint for the model to indicate the potential functionality of the code solution. The first thing that we evaluated is the different by using different number of in-context examples. So like an example is basically this input but filled with the canonical code solution, basically to show the model the input queries and also the canonical solution. And we're trying to use like 0, 1, 2, or 3 different in-context examples. And that we find that like different models have different behaviors, that for the 001 series models, we observe a like increase of performance when we're adding more in context examples. That's clearer for the Cushman 001, which might be the smaller and the earliest version of CODEX. But for the DaVinci 001 model, when it sort of reaches a plateau where like adding 1 or 2 in context examples, there's a slight drop in the performance when we're adding more examples such as 3. And differently for the DaVinci 002 model, which is probably the strongest version, that we find that adding more in context examples does not necessarily help. So like, for example, you can see that here we're adding 1 in context example, the performance actually drops a bit. Like when we're adding more examples, it is slightly increasing, but like not by a large margin as compared to adding 0 examples. Which is a like interesting finding that when the model is like strong enough, is probably being trained on many of this code examples, that it does not necessarily need examples to like exemplify what it needs to predict. And the second ablation study is we compare adding different number of test cases in the docstring. In the baseline setting, we're adding 0 test cases in the docstring, but it seems like it might help if we give some like additional hints on its execution, like input output examples. So we're trying to add like 0, 1, or add all of the test cases that we annotated into the docstring, basically formatted as here on the top illustration. And another interesting finding is that we find that for all 4 languages, that adding 1 test case in the example is almost as good as adding all of them, and sometimes better, especially for the Spanish. So like in general, adding test cases is outperforming adding non-test cases, by a large margin, but you sort of only need one example to show what might be a potential input-output use case for this code solution to help the model. And adding more only gives you very little further improvement. Another like thing that we observed of this test cases is that like sometimes they only change the value and the overall format is similar to, so that might be another intuitive explanation of why adding one example is good enough, because when you're adding more, their format is basically the same and it conveys like little additional information. But this is a good thing, because now we don't have to put all the test cases that we have. We can only put one example into the doc string, and it could also give us like good enough performance. So yeah, I think these are all of the experiments that we have done and analyzed for our work. And I think I'll start here and to see if there's any more questions. I'm happy to answer.
All right. So thank you, Zora, for presentation. And once again, folks, please raise your hand. Please raise the questions to the chat. And while people are making up their minds, I would like to ask a couple of questions of my own. First, could you be so kind as to go to the slide with the model comparison, like one of the very first model comparison slides, where you shown that basically CODEGEN, yeah, this one. So here I have a question. Which of the two, in your opinion, do you think is right? Option one, CODEX leveraged data to improve open domain training. And basically, if we train the model in the best possible way that is available right now, there's gonna be the gap. Option number two is that technically we could have similar open and closed domain performance as for CODEGEN, but it's just that the CODEGEN model is prepared not as good as the CODEX model, and it's actually closed domain performance for CODEX that is lacking. What do you think is of the two is right?
I might be a bit I probably didn't understand the two options very clearly.
Okay.
So like
sorry, let me just rephrase. So let's look at open versus closed domain for CODEX and for CODEGEN. Do you think CODEX was trained so good on the open domain, but not so good on the closed domain? So it could be easily, well, somewhat easily improved to become better on closed domain or on open domain? Or is it that the reverse, that naturally when we train a model, the open domain performance is always going to be way better if we make use of the available data properly?
Yeah, so like for the CODEX performance, one is that because the like huge gap between open and closed domain performance could be because that CODEX is not very well trained on open domain coding queries. Another is that naturally like the performance on open domain would be lower than the closed domain, right? I think yeah, that's a good question. I feel like at least for human programmers, that writing open domain code, which involves complex usage of external libraries, is definitely harder than just using built-in Python grammars. Because for one, you need to learn to use many different libraries as compared to only the like definite set of operations that are built into the Python grammar. But like, I'm not sure, like if, I think there's still a chance that Codex could do better on open domain problems. I think one thing is that, like, I don't necessarily think that Codex behavior have to be aligned to how human programmers perform on open and closed domain coding queries. Like it might be hard for humans because we cannot remember everything and we have to refer to the documentation of each library. But for Codex, you can like at least alleviate that issue by training on more open domain coding queries. And you can also like refer to your documentation where other use cases and try to come up with better solutions for those open domain coding queries. I think it's more, it might be better to like set the expectation for this model performance by how much we need models to help with this coding queries. For example, as human programmers, we're like using the help with a programming assistant such as GitHub Copilot, we might need more help on the open domain coding queries. And that to do that, a good programming assistant might need to perform better on open domain coding queries. And we can achieve that by like more creating better like training data or like building more effective benchmark to evaluate models to like reach that goal. So I think it's a like back to the question, I think it might be both. Like it's not as well trained on open domain, and also like open domain queries naturally hard to learn. But I do think that it might be better, since we need more help on the open domain coding queries, that like this language models could learn to at least we could like collect more data to more intentionally train on these libraries for like more effective usage of these models.
All right. Okay. Thank you. Thank you very much. A question also related to this graph. I was surprised to see that, say, well, Russian and Japanese queries, and well, Spanish as well, in many cases, modules perform better with like with these languages than with English. It's kind of surprising for me because I would naively expect there is way more data in English than for the rest of the languages. Do you have any idea for why this could be the case?
Yeah, we're also surprised by this result at first, because like in general, you would expect that like English is the most widely used language for programmers, and that might outperform other languages. One reason that we suspect is that all those like training, for example, we know the training data of CODEGEN that is scraped from like the GitHub and the web. So it might contain, it includes like code files written with natural language intents in other different languages. So it might be exposed to like data like this. So it could achieve a good performance on this like non-English languages. And another influencing factor might be because this like different the sets for each language is different, because we're like individually collecting them from different forms of different languages. So they also have different distribution on the libraries that involved, where the samples that are like being asked. So this might also lead to, for example, for the Russian subset, it might more frequently contain those data sets data science libraries such as NumPy and Pandas, which are very frequently appearing in the Stack Overflow data, and it might be easier for the model to generate those solutions. But that is like also built on the fact that language models can understand the natural language intent in non-English languages, which is like I think an impressive observation from this both language models.
Okay.
Any other questions or comments?
Oh yeah. Sorry, I was just muted. I had an idea. Yeah, I had an idea that there might be just so many samples of code with English description, and not always the descriptions are perfect, that it might be that the model is a little bit swarmed with all these descriptions. Like there are, I don't know, tens of thousands very similar problems which are solved with, I don't know, requests library. And then the model is trained on all these examples. And basically it turns out that, when we ask model to do something, it produces the code which is informed by all these examples. While for other languages, there might be not so many examples, and the difference between the code is bigger. Like the semantic difference between the examples is bigger. So it might be that the model can find something more relevant. But this idea also hinges on how does model transforms, say, Russian into code. Does it translate Russian into English and then gets code? Well, I mean, I'm being very imprecise here, but still, like, how does it work? And on that, I don't have any idea.
Yeah, so are you saying that it might be like, say, there are only, say, like less libraries involved in this Russian subset, so that the models might be easy to find similar samples or code examples for that library because there are less diversity, so it's easier for them to learn?
Not exactly. Just less code samples, so it would be easier for the model to find something similar and not to produce something which is just a little bit off. Because when we grade by facet 1, just having even a small mistake makes the program fail.
Like, what do you mean by the small mistakes?
I mean, like, if there is like a small mistake in how to use API, I don't know, there is like a decent size piece of code, like, I don't know, 20 lines, but then at a certain point there is, I don't know, like they call it as they address it as an array or as a list, but in fact this entity is a dictionary, then everything goes down, even though it's like, it would be okay. And this could happen if there are like many different pieces of code which kind of look similar, but yeah, never mind. This idea is not fully fleshed. Any other questions, folks, or shall I continue with mine?
Yeah, hi. Perhaps I can ask a question. Thank you for the talk. I have a question about the slide with the graphs with the graph with different libraries. I was just wondering if you observed any distinguishing clusters, perhaps, of libraries. Particularly, what I have in mind, intuitively, it might seem that, for example, standard Python libraries like requests, maybe they are more frequent or just more easier to understand than some third-party libraries or something like that. Or perhaps there were similar performance for some web libraries libraries or some data science libraries or something like that?
Mm-hmm. Yeah, that's a great question. So like we tried to do like some like clustering of this, like one possible clustering that we can do for this library is based on like their intended usage. For example, there are some data science libraries such as NumPy and Pandas. There are some like web request libraries such as HTTP or like requests. But like we didn't necessarily observe very like we didn't observe very like a very clear correlation of like say between different, say for example if libraries of this similar topic would have similar performance. One like limitation could be that our data sets still like not good enough and not covering all the possible use cases for all these different libraries. So it's not like a very comprehensive evaluation on how models perform on this data set. And another is like as I listed here, there are like many more potential factors that might affect the model performance. And even though they are like intended for the same purpose, such as for example, the like pandas torch and could all be like for the data science purpose. But like torch might involve more functionalities and more complex usage as compared to the functions or like the main functions that people use for pandas. So even though they're like could be clustered together by their topics, it's not like it's hard to find the clear reason why they're like they might still have different performance. So yeah, that's a like interesting problem that like to further investigate.
One more question that I had on this slide. Do you have an idea how to define library complexity from a somewhat formal point of view? I think I understand what you want to say, but I'm not sure how would what would be the proper definition.
Mm-hmm. Yeah, I think this is also a good question. Like there is no formal, at least no one has like claimed to have a formal definition of the complexity. But one way they're like thinking of measuring the complexity is like to see how many different functions are supported by that library. That could be like a numerical measure of how complex that is. And like furthermore, say for each function, how many arguments are involved? Like, do you need to specify to like call that function? That's also like a factor that affects the complexity. More intuitively, the more arguments that you need to specify, the more complex that function is. Yeah, I think that's it. Like two main factors that I could think of related to the library complexity.
Oh, okay, thank you. Maybe one more idea that I have is that we all care not only about the possible set of functions, but also about how often are these functions used. So say if you have 1,000 different functions, but people only use 3 of them and the rest of them are never used, we could maybe effectively treat this library as only having 3 functions and the rest of functionality is basically irrelevant. Would you agree?
Yeah, yeah.
All right, folks. Any other questions from the audience? All right. Okay. As there are no further questions, could you please just move forwards to the slide where you compare different, yeah, this one, compare different metrics. So I know that at your lab, you developed, well, maybe not literally you, but the team you work in developed a new metric called burst score. Did you try it on to evaluate ODEX, model performance on ODEX? Does it work better than the rest of the metrics? Maybe not you, but your colleagues.
You mean the code score?
Yes.
Oh, yeah, this is actually the author of code score. Like he was asking, have we evaluated the CODEX ODEX on code score? The answer is we didn't, because we haven't like started. We're like haven't finalized the code score.
It was basically like COBRA score came out after ODEX was out.
Yeah, so like when we're publishing this data set, we didn't evaluate the COBRA score.
Yeah, but maybe you did that afterwards. That's why I'm asking. I know that CODEX score was published later, but maybe you like tried something like that. And I think there is Xuyan on yeah, you saw maybe Xuyan did try that. It would be interesting to know whether there is whether you have any insight about CODEX score.
Yeah, I actually am not sure they evaluate. I think they probably didn't evaluate on ODEX, but yeah, I think their like main takeaway for the CODEX score is that it's like better than lexical-based metrics to capture the semantic similarity between two code solutions. So they're like have higher correlation with a human evaluation, which should also have a like distant correlation with the execution rate. But yeah, that's a good suggestion. We can like also evaluate ODEX by using CODEX score to see if like that can provide any additional insights. But yeah, so far we don't have any clear results on that.
Okay, thank you. And related question for the graph on the variance between passed and failed. So do you have any insight on how this graph should look ideally? Because my point is that, well, okay, obviously, in my opinion, everything that does have a pass should probably have a score of 1. But I mean, I guess we also should have some data. A proper metric should also fill up the rest of the like the rest of the line, because the code could be almost perfect and need only little fixes. So did you think of maybe trying to make some, I don't know, I admire the graph, and the graph is really telling many things, but did you have any idea on how to summarize this graph into numbers that would say that, okay, blue is very bad and it gets a score of, I don't know, 1.2 out of 10, while, I don't know, GRF is slightly better and gets a score of 9.7 out of 10. Do you have any suggestions on that?
Yeah, I think, yeah, first for like that, like the blue scores in the past examples, that like most of the examples are like having a full blue score, which is 1, but there are like for other cases that like they did not predict the exact same prediction, but also like alternative solution that could correctly solve the problem. So that's for the like other cases for the past scores. And like we also like coming back to the like higher predictions of having a higher blue score that might be better, like that might indicate an easier fix for like easier fix on the code prediction. I agree with that, and we also like have similar observations from our case study that often like roughly for those samples with a blue score higher than 0.7 or 0.8, they're very similar to the like listed reference code solution, but like there are sometimes like slight difference in other, say they use the like wrong function of that library, but all the arguments are in place and they're correct. So the only thing they need to fix is to change the function name. And other cases might be there involves some like string manipulation and the predicted code copied the string wrong. So that could lead to execution errors, but it could be simply fixed by just like checking, like just recopying the like string indicated. So I agree that like the lexical, like we think that it might be better to like continue evaluating on lexical based methods because they still indicate some things like their surface form similarity, and that could like indicate a like easier fix on your code solution. But also we probably also need to evaluate the execution to see whether it's functionally correct. So I think the joint of those different evaluations are like should be like better than just simply choosing one of them.
Okay, thank you. Once again, folks, any more questions?
Yeah, I have a question.
Yeah.
Can you put the slide with the dataset collection and construction?
Which this one?
Next one.
This one?
Yeah, that one. Yes. Is it right that it's always clearly stated which library we are trying to use in the code example? And so it might be in the natural language query, or this library might be like in import section of the code file that we are get to the model or something. And for example, if we have a function that calculates the sum of an array, we can use a NumPy array and NumPy sum function or built-in Python sum function. Both will be working, but the one example will be using like open domain as we intend to do, and the other will be like is also solution, but it will use like closed domain techniques for it.
Mm-hmm.
And also
yeah, that's it.
Yeah,
please finish.
Yeah, that's it.
Mm-hmm. Yeah, that's a good question. Like, just to rephrase the question as, are you asking, for example, for some, say the sum operation, you can either like use it open domain numpy.sum function, but also use it like Python built-in sum function, which the former is an open domain query, but the latter is a closed domain coding query, right?
Yes, yes.
Yeah,
And both
that's
will
a
be
great question.
pass the tests, which
Yeah, that's the like issue that we also was considering, like how to deal with when we're creating the data sets. Like so like the decision that the strategy that we used is we follow the like to choose which sum function that we need to use. For example, here, if we choose numpy.sum or like Python built-in sum, we first refer to the natural language instance. As you can see from this example, that it actually like indicates like to sum over all rows of a 2D NumPy array. So which is the clear indication of the input variable A is actually a NumPy array that to do like it's not necessarily it's not necessarily that the code solution have to use the numpy.sum, but like if you could use the Python built-in sum to like also sum over the rows and output a NumPy array that is the result, where like our execution-based evaluation could like evaluate those as correct. But like with the indication of the NumPy array, if I'm not sure if that sum works for this example, but like if the Python built-in sum doesn't work, you might have to like only use a NumPy dot sum to correctly realize this natural language intent.
Yeah,
Yeah.
in this case, it doesn't work. It won't work. And do you put the import, like import NumPy as NP something in the context of the query also, or not?
In the default setting, we didn't. So like, as you can see from the example here, that like for the only way that we include test examples where includes the NumPy array input is the like example test cases, that our default setting is input 0 test case. So it's like without this line, and the model only sees the function signatures and the natural language intent. But like the intent here, the NumPy array should like indicate the usage of the NumPy library. So that's why like model might work for this example.
Yeah. And I guess it is necessary to put imports in the context, because, for example, I can import NumPy array, not NumPy as an NP, or I can just import NumPy, and the code should be different in these two examples. And also, if we train the model to use some library to do something, and then we put it in the context which didn't have a library installed, it will produce code that didn't work. So
yeah, so for the first part, you mean like we can put like this line of import NumPy as NP, or like just the import expression of this library to the doc string and the input, so that like the model could know what to use, right? That we have also tried that, but we like end up didn't use that, include that in the default setting, because that sort of like simplifies the question, because now you're like telling the model which function library to use. Like the results when like adding the like import expression into the context could like lead to better performance, but this is not necessarily a like realistic use case when you're trying to predict a piece of code, because if you don't know the solution, then like for example, assume like you're a person asking a question on Stack Overflow, they actually don't know how to solve this problem, then like you may also don't know which library to use. So like at prediction time, it's more like realistic to not knowing what library to use, like not disclose any like partial answers. But like it also challenges the model more. Yeah, but like comparing like adding or not adding the import expression, adding that into the doc string is definitely lead to better performance. But like we think that it might be better to like not include that, since that disclose too much information. And sometimes it would also make the model less likely to predict alternative solutions. Say, for example, if like torch.sum also works for this setting, and the model, another valid solution is like torch.sum A, but if you specify which library to use, the model is more likely to predict that alternative solution.
Yeah.
I remember there's a second question, but could you repeat that?
Oh, well, I guess in terms of Stack Overflow questions, you're correct. In case the user didn't know which library to use, but when we work in our code editor knows which library we have installed in our environment, and also it also knows which library we already imported in our file. So maybe it's like different contexts, but for the context of a code editor, we should include all imports to the queries.
Yeah. I think that's also a reasonable use case. Yeah, I think because like different people are using code generation models for different purposes. Like in the last answer, I sort of assumed like maybe we're helping like people who don't know how to write code. So like the assumption is sort of like they don't know which library should use. But like it might be another story for proficient programmers. Say like, you already have written half of the file and you also specify the libraries where you know which libraries to use. So like, yeah, we might need the model to perform under different modes, or like they can take in different contexts when they're like working with different end users. Like for example, proficient programmers were like people who don't know how to code. Yeah, I think, yeah, in general, it's like interesting to like investigate or compare different settings to see how models could tailor to each of those different scenarios.
Yeah, and maybe it's also like an idea for data augmentation. For example, import numpy as NP and import numpy and ask the model to complete the rest. For example, if it sees numpy usage as np.array and we modify the import, we could see if the model just memorizing all of it or quote unquote understands it.
Yeah, that's a interesting thing to do. Yeah. There are some works that try to like slightly rewrite where like just as you said, like change the input of the task case and like slightly make changes in their context to probe whether model actually remembers, like was only memorizing that piece of code, or like could actually understand and generalize to write that solution. Yeah.
Yeah.
Thank you. So, folks, any further questions? We only have like 5 minutes left or so. So maybe one or two last questions, if anybody has them. Okay, in this case, I will grab the floor once again. So could you please move on towards the end of the presentation, where you discussed the further no, one slide further, if I, or maybe I forgot. That one. Yeah, sorry. So yeah, this one for the model performance indeed. So I I had a question here about the test cases and in context examples. So do you think something else in docstring could be also useful apart from in context examples, test cases? Because I mean, if I would be looking at a docstring, I would say that a proper description in human language is also good, but this is incredibly hard to measure technically and formally, I believe. Do you think any other things could be checked for in, say, I don't know, ablation studies or stuff like that? It's not like you have your work has a shortcoming. It's just what else could be useful for a model, in your opinion?
Yeah. A few other things like that we have tried like to altering the docstring is probably not docstring, but more on the function context side, is we like change the function name. Like we also try to like, because now it's like a very generic constant string for the function name, which is function. And we also try to use like replace it with more semantically meaningful function names, such as for this example, we'll just name the function such as convert string to float, which might indicate more on the like functionality if the model is supposed to predict, but that sort of gives like very little improvement and sometimes drops. One is because we're like using the heuristic approach to create the function name by like concatenating the first few words, and that heuristic may not work as well for other non-English languages. But also like it's sort of, it is also like that function names also conveys similar information to the text docstring here. So it might not provide any additional information. Another interesting point is that, like you mentioned, the like way that we specify or phrase the intent could also affect the model performance. Like one critical factor is that we find is that we specify the variable names so that like the model is clear to, the model knows like which variables should be inputted or outputted. So it helps with the like generating the function. And like more ambiguous side is like how you write the natural language sentence to frame the intent that you want the model to implement. That is like still like an open problem, I think. And we're like also recently discussing like when you're phrasing a question from the like in the most abstract way, that the model is like, it might be very hard for the model to generate a prediction, but you're like framing that in very specific manner. One good example is that in the, I think, NTPB dataset published along with the CODEGEN model, and there like each turn of their specific natural language intent, those can be almost like very well mapped to the code implementation. That could, of course, lead to better model performance, but like it's like a bit artificial because no one actually could phrase instruction like that. And even for programmers, it might be more efficient to directly write the code if you could frame an intent in such specificity. So, but yeah, in general, I think this is an interesting but also open problem to study, like to which abstract level should we phrase our intent and what is the best way of like writing the natural language to help the model generate the code.
Oh, yeah, I agree. And I believe it's also very practical. Like if I'm a software engineer and given that we have access to CODEX and ChatGPT and stuff, I would be really interested to know how to leverage them best. So that's indeed a very important problem. One small follow-up. In some cases, you can write types in Python. did you have a chance to check whether having types it makes any difference? Like if there is if the types are written explicitly, does the model perform better for some pieces of I don't know, for some pieces of code, does model performs better or worse?
Yeah, that's a good point, but we didn't check that. One reason is that for many of our samples that the type of the variable is not like strictly defined. For example, if we like we have a sample to sort a list, that could be a list of integers or a list of strings. And we find it hard to like strictly specify the type of that. But I think we haven't tried this, but I think this might be an interesting thing to do to try to add like the type signature of this input output examples and see if that improves the model performance. My intuition is that it could improve like the performance because it's like conveying more information of the function. Yeah.
All right. Thank
No,
you.
I'm just saying thanks.
Yeah. So yeah, thank you so much. So, folks, I believe our time is up. So once again, thank you everyone for coming. Zora, thank you very much for giving this talk and answering to all of our questions. And please let me know if you would like if there were some issues during the talk, stuff like that. Please let me know so we make our seminars better. And our next seminar is gonna be in 1 month, early May, and the first announcement would be available at our meetup page. So please subscribe and come to our next seminars.